So now that we've talked about inductance and self-inductance, it's time to talk about the energy that is stored in magnetic fields. Okay, so how are we going to do this? We're going to think about the total amount of work that needs to be done in order to build up a current in a certain loop. So how does that go? You remember that the power in a circuit is voltage times current. So the power is really the differential amount of work done per unit time. And in our case, voltage is just minus the EMF, because the EMF just represents the kind of voltage you have to work against when you try to pump up additional current. So we multiply this by the current. And now using the formula for the self-inductance that we have, this just becomes L times I times di dt. Okay, now so we can just integrate this in time, and what we obtain is that the total amount of work that we need to do is just 1/2 the self-inductance times current squared. Okay, so there's perhaps a nicer way to do this. So nicer way, which is generalizable to whatever configuration you have, be that surface, volume currents, and whatnot. So we had an equation for the flux through the loop, and in the notes that I wrote up for you, this is equation 7.25, which just tells us that the flux is phi times Li, mutual self-inductance times I, and we can just complement that by saying that the flux phi is the integral over the surface of B dotted into dA, which is the integral over the surface of the curl of the vector potential dotted into dA, which is, by Stokes, the integral over the closed path delimiting the surface of A dotted into dL. Okay. So what that tells us is that L times I is just the integral of A dotted into dL over the path. Okay. And also the total work we've done, so the energy stored in this whole thing, is 1/2 times I times the integral of A dotted into dL. Okay, and really what we can do is just write it like this for this configuration. It becomes the integral of A dotted into the current vector, okay, times the length element of the loop. Okay, so now I've just rewritten the current as a vector along the dL that we have here. Okay, so this immediately generalizes to volume currents, because you see, instead of just integrating a line current along a line, I can just say now I'm integrating over the volume with the volume current density, right? So I would just have that the total work, total energy is 1/2 the integral now over volume of A dotted into the current density J, okay, times the volume element d tau. Okay. Now, I can use Ampere's law. Okay, to replace J by 1 over mu 0 times the curl of B. Okay. Integral over my volume of A dotted into the curl of B. Okay, times d tau. And now what I can do is use one of the product rules, which in Griffiths's inside jacket cover is product rule 6, which is that the divergence of two vector fields crossed into each other is the second one dotted into the divergence of the first vector field minus A dotted into the curl of the second. Hang on, so there's just a little mistake here. So this is not a dot, right? This is just a cross product. Yeah. Okay. So where does that leave us? That allows us to write that A dotted into curl B is equal to B dotted into B minus the divergence of A crossed into B. Okay, and now I can just use this in here. To rewrite my total work as a sum of two terms. So the first term is just 1 over 2 mu 0 with now the integral over the volume, yeah, d tau, of just B squared, B dotted into B. And now I have 1 over 2 mu 0. Again, the integral over my volume of now the divergence of A crossed B. Okay, again with d tau. But really, this term here, using the divergence theorem, I can rewrite as a surface integral. Okay, of my surface element dotted into the vector A cross B. Okay, but this I can all put to 0 if I put surface at infinity. Okay. So what we get is that the energy stored in magnetic fields sorry, my computer is really hiccuping quite seriously here. The energy stored in magnetic fields, let's write it as mag, is just 1 over 2 mu 0 integral over all space, that's a nice integral sign, d tau, of B squared. Okay? And a reminder, for E fields, we had that the energy stored in the electrical fields was equal to epsilon 0 over 2 with the integral over my volume of E squared. So you see the nice parallel between the two. Okay, so these equations, at least in vacuum, give you the energy stored in the two types of fields that that we have. Okay, it's quite revealing expression, a nice little expression for this energy. This is going to be useful in a number of occasions later on. Okay, so as an example to maybe look at by yourself. Again, I'm not going to do this in detail here because you find all the details in the book. Have a look at example 7.13, which is the energy stored in a coaxial cable. Okay, it's just a question of using the formula that you know for the magnetic field inside such a coaxial cable, and then just integrating over space to get it. But I'll let you have a look at this by yourselves because it's quite straightforward. Yeah.